Today we're going to talk about boundary value problems. And the last week we were talking about these initial value problems. So I'm going to have this IVP over here. And it was this initial, so we had something to do with the initial value. So at y equals 0, okay, given that time is maybe this way right here, we knew about this point right here. And we also had some sort of function, so we could kind of figure out the slope for a particular time segment, and then we figure out the next spot. And then we had another slope, and another slope, and another slope, and another slope. And slowly but surely we were marching forward in time to get some sort of profile of y, and therefore we were able to solve for y at all times by marching forward in time or in x or what have you. Boundary value problems are similar, except that we have the initial point and we have a final point. Okay, so these are the boundaries, which means then that at time 0 and at time, let's say, I don't know, 10, okay, or maybe this is x, so at point 0 and at point 10, we know the final point right here, so I'll call this y10. And we have this point right here, which is y0. Okay, this axis is, of course, y. And what we want to do then is try to figure out, well, what is the profile, okay, between these two endpoints, between these two boundaries, all right? And that is what boundary value problems are all about. So this is the BVP side, and I'll sometimes say BVP to mean boundary value problems. And I'll refer back, of course, to the initial value problems from last week, which is similar but a little different. In that sense, of course, we have this as our initial condition. So we might have an initial condition for each order of the ODE. And down here, we're going to have boundary conditions. Okay, and we need to have, of course, one for every order as well. We'll talk a little bit about that later on. All right. Well, as I just mentioned, if we have an nth order ODE, then we need n conditions, okay, to get a unique solution. All right, very similar, right, to those n equations for n unknown sort of idea. And so if we have a second order ordinary differential equation, we need to have two initial conditions to, well, solve the sort of breakup into two first order ordinary differential equations like we solved last week. And similar with boundary value problems, there are reasons and ways that we need to extract out those two initial conditions, or of course those n conditions, to solve for all the unknowns. All right, well, of course, if all the conditions are specified, you know, at that same independent variable, then we have, well, back to the default initial value problems, or IVP. But as I mentioned, if we have the extreme points or boundaries, well, then we have the boundary value problem. Okay, and the solution strategies for these classes of problems are different, but of course they use similar sort of principles, and so we'll talk about those differences here in the next little bit of time. All right, so what kind of applications? Well, a lot of times heat transfer analyses are in the domain of boundary value problems because we might know something about the initial heat condition on the inside of a house. We might know the initial situation of the heat outside of the house, and we know then that, of course, the continuous function in between those two extremes is going to be satisfied by the insulation and the drywall and other elements in between those two extremes. Effectively, we want to figure out what the heat profile is throughout that wall. Same sort of thing with beam bending analyses. Quite often we have some constraints or points at two ends of the beam. So think of a bridge, for example. We know, and hopefully know, that the two sides of a bridge are not going to be moving with respect to maybe the middle of the bridge, which might be deflected a little bit up and down or displaced to some degree. And so we want to know kind of what the profile of the bridge is in between those two boundary conditions. And then similar with fluid analyses and chemical diffusion, we might know something about the densities or the gradients or these types of things, but we don't know exactly what's in between those 2 points, and so we use boundary value problems to perform those type of analyses as well. All right, so let's talk about a first example of a boundary value problem. And as I mentioned, we have kind of this a wall inside of our house that has insulation, and so this sort of model right here is kind of representative of that. in the sense that we have a rod, okay, and this is like a 1D problem, so we have this little rod right here, okay, and we know something about the temperature at this side of the rod and something right here at this side of the rod, okay, and so we have T1, okay, down here it's at T0, so now we have this X point right here, something about X equals 0, okay, and we know the temperature at this. We also know the temperature at X equals L, T2. Okay, so these down here are our two boundary conditions. And now we want to know, well, what effectively is the profile of the temperature along this rod right here. All right, well, there's a few other things in this simplified sort of model. We also have sort of an ambient temperature. So if we do have the temperature inside this rod, and if the rod is hotter than the ambient temperature, well, we're going to actually see some heat flux leave that rod. Okay, and so you'll learn more about this in future classes if you haven't already taken it. But effectively, there's one simplified model, such as this one, which kind of shows this sort of heat transfer along this rod from T1 to T2. All right, so you'll notice then that, of course, that it's a second order ordinary differential equation. The variable of interest is the temperature along that rod. We are, of course, moving spatially, so we take it with respect to x. And then we've got some other terms right here. Okay, in particular, we've got the heat transfer coefficient h, okay, which is going to be constant. Effectively, that's representative of the properties of the rod. Okay, and then we have the ambient temperature, and so of course, if the ambient temperature is the same as the temperature of the rod, well, this is going to be equal and 0, and there's not going to be any sort of heat transfer, okay, from the rod to the ambient temperature. So we have this, again, simplified sort of model, and now we want to do is figure out what t is for all time, or rather, in this case, what t is for all x. Okay, we have the boundary conditions. I know what's right here, and I know what's right here, but I don't know, okay, what the temperature profile is along this rod. All right, well, we've got this ordinary differential equation. It's a second order, and we're going to use what's called the shooting method to hopefully try to solve for t at all x's. Okay, well, the shooting method is a good place to start because we've got some experience with the initial value problem side of things. And so the way that we take it is that we take this boundary value problem. Okay, here's boundary 1, here's boundary number 2. I've actually replaced T1 and T2 with 40 and 200 degrees. Okay, we want to convert this boundary value problem, these two boundary condition here, okay, to an IVP, or an initial value problem, by initially ignoring the boundary condition at the end. Okay, so we're just going to ignore this right here. So essentially, right, we've got that initial condition, and we've got this one right here at the other end. We don't know where it is. Okay, well, we know what value it is. Okay, it's 200, so this is going to be 200. Okay, this right here is going to be 40. Okay, but we're going to ignore this one initially. Okay, so if we're ignoring it, then we're just going to try to solve it like initial value problem. And so we're going to march forward in time, we're going to march forward in x, we're going to march forward in whatever that independent variable is, and then we'll see, okay, if we hit our result. All right, so we solve over the domain. In this particular case, it's x. So we go from x0 to x10. We're going to use another, Euler or Hoynes method, RK4 or ODE45. Whoops. ODE45, etc. And in general, this second boundary condition is not going to be satisfied. We might miss it. Okay, so we're going to keep on trying with different initial slopes until we hit this point up here. So we're going to try down here, and we'll march forward in time, and we might miss it. Then we're going to try something different, and we might miss it as well. And slowly but surely, we're going to hopefully home in on the result right here. Okay, and if we hit it, well, then this, of course, is the solution. So this shooting method then is just that. We are shooting different shots, okay, starting from our one boundary condition, okay, and we're shooting shots, okay, multiple times, and hopefully trying to hit, well, eventually this boundary condition. So all these other ones are fails, but one of them, of course, is going to be good, and so we have to kind of keep on guessing, okay, until we hit that shot. Now, if by chance it's linear, all right, we can do linear interpolation, and of course we talked about that a couple of lectures ago, because essentially, if by chance, okay, we have, this is our initial boundary condition right here, and this is our final one right here, And if we, shoot here and then we shoot another one right here, well, we can interpolate right here. Okay, so after these two wrong choices, we can choose one halfway in between and it's going to hit exactly in the middle. And we'll show some examples of that as well. Okay, but for nonlinear ODEs, several iterations are likely required. So there might be something like this, where we have to do 10, 15, 20, who knows? Okay. Now, the pros of the shooting method are that there's really nothing new to learn. Okay, we just use the existing methods, whether it's Hoyne's method or Euler's method or ODE45, and we just apply it and we shoot away. And if we miss, well, we keep on shooting, and eventually we're going to hit our target. Okay, it's very fast for linear ODEs in the sense that we only need 2 guesses. Okay, and we'll talk about kind of those guesses later on, because we have to kind of guess that first slope. Okay, we'll talk a little bit about that a little later. It's very fast for linear ODEs. Okay, but of course, if it's not linear and if it's a higher order ODEs, well, we got some problems. It can be very tedious. So, for example, if we have a third order ODE, well, then we're going to have to assume maybe a whole bunch of different initial conditions. Okay, and the solutions can be very sensitive to the initial conditions in the sense that it can be difficult to converge if by chance we have a bad guess. So there's some downsides to the shooting method, but of course there are some pros as well. Just like all the other numerical methods in this class, there's pros and cons, and as engineers, we all need to know when we need to apply these and when we should avoid them and use other methods. All right, so we're getting close to the example, but let's just kind of talk a little bit about how to program the shooting method inside of MATLAB. Well, the first step is to convert to a first order. Nothing new there. Okay, so here we have our second order ordinary differential equation converted into a system of 2 first order ordinary differential equations, one here and one here. All right, so of course we're after t for all time, or rather t for all x, okay, and so we're going to make a little substitution for this one, and then of course we're going to pop this into this guy right here, okay, and then we're going to isolate these terms and make sure that everything on the left hand side is a derivative. Okay, once we have that, then we can use any method. In this particular example, I'm going to use Euler. Okay, and so hopefully you've seen Euler before, but effectively we have some sort of initial condition right here, and then we're going to add on a little bit of a slope times a little bit of time, or a little bit of x, or what have you. And as a result, these two terms kind of cancel each other out, and so we're taking a t, adding a little bit more t, and then we're going to get, well, the next t. And we have to do that for the y dimension as well. So essentially, right, we take this equation, we pop it over here, okay, and then we take these two, or rather at least this one right here, okay, and we're going to pop that over here when I is equal to 0. Okay, that's of course when x is equal to 0, the very first initial condition. And this guy right here is just useful for a check. Okay, we don't use this one for anything except for checking if our shooting method worked out really well. Okay, so let's take a look at the other equation right here. Well, we know what this value is already. Okay, that's delta x. Okay, we don't need to worry about this one, but now right here, yi is the problem. Okay, and that's what we have to guess in our third step. We have to guess what that first yi is. Okay, effectively, we don't know what the first y is. We're not given it in the problem. Okay, we're given this initial condition and this boundary condition, rather this end condition, but we're not given y0. Okay. Not given. Okay, so as a result, we have to guess this initial y0. Okay, so we start with some sort of y0 value. Okay, and then we march forward in time, use Euler's, what have you, and then we check to see if this t10 is correct. Okay, if it's not, well, then we have to make another guess for yi, and then we check t10 to see if it's correct, to see if it's 200 over here, and we keep on going. And of course, if it's linear, we can kind of be smart and try to figure out what that guess is. But if not, then we're going to have to spend a lot of time to try to figure out what that y is. All right, so writing code. This is kind of the process that I'll discuss during my example, but effectively just to kind of cover it, we need to ask ourselves, what variables do we know at the start? Okay, and how are they going to be initialized? What do we know about the problem? Okay, what functions are required? Can we get by with anonymous functions, or do we need to do a function file that's separate from our main function? Okay, what variables do we want to know? Okay, and what's the process for determining them? What loops do we need? Okay, what sort of method are we going to implement? What's done inside and outside? And then, of course, what and how will we output? In terms of the software, and of course we'll talk a little bit more about this, but I'm just going to walk through this little flow block diagram to kind of explain what I'll do in the example here in just a few more minutes. But effectively, just like we did before, we need to initialize our variables. Okay. In this particular case, this is a little different than initial value problems because we need to make a guess for that t prime. Okay. In the previous example, it was known as y0. That's because y was equal to dt dx, which is equal to t prime. All right, so we have to make that sort of guess. And then, right, we got to go through this little while loop right here. Okay, and it's while tcalc, okay, tcalc minus t10, okay, that's that second boundary condition right here. That's that boundary condition on the other end. Okay, if the difference between those two values is greater than EPS, okay, machine epsilon or some sort of really small value, we'll talk about EPS here in a second when I go to MATLAB. Okay, if that value is greater, well then we need to keep on going because we haven't converged yet. Okay, and so tcalc then is going to be the value that we calculate at the other end. Okay, so it's going to be based upon our initial value problem during the shooting method. It's going to be what we'd expect T10 to be. Okay. Now, of course, if this inequality, right, if the left-hand side is greater than EPS, well, then we need to keep on going because we haven't gotten some sort of value that's close to 0 and we're not done. We haven't converged. So we, of course, calculate this tcalc using Euler, and then we can use Newton-Raphson, okay, in a specialized sort of method, and we'll use F0, okay, to talk about how we can use Newton-Raphson in F0 to find the next, okay, t prime. All right, once we have that, well, then we go back up, okay, and we do it all over again, and eventually we're going to kind of converge. All right, so now I'm going to go off to MATLAB, and we'll explain this process, hopefully with a bunch of code, and the theory that we had just discussed will hopefully become more clear as we go through some examples.